Okay, Assalamualaikum warahmatullahi wabarakatuh and good day to all. We continue our session to session 3, diesel cycle in part 3. Okay, for example 2.4, let's read together an air standard diesel cycle. So it is a diesel cycle, has a compression ratio of 16. So RV equals 16 and a cut-off ratio of 2. So we have RC equal 2. At the beginning of the compression process, the air is at 95 kilopascal and 27 degrees Celsius. So at P1 is equal 95 kilopascal and temperature at 1, beginning of the compression process, is 27 degrees Celsius. So in this example, they need us to determine the temperature after the heat addition process, which means temperature after heat addition process. The heat addition process occur from 2 to 3. So after heat addition process is 3. So temperature at 3. B is the thermal efficiency, and the last one is mean effective pressure. So in these questions, they ask you to assume the constant specific heats for air at room. Okay, now let us try to solve this problem. Example 2.4. Okay, now at first let's us try to draw the PV diagram of the diesel cycle. We know that it's a diesel cycle, so pressure is constant at 2 and 3, and then okay, it starts from compression process in 1, 2 here, 3, 4. So we need to know where is the heat addition process occurred. Q in is at 2 and 3, where the pressure is constant. This is what you need to be careful. And then Q out is at 4 to 1. So this one, 3 to 4 and 1 to 2 is isentropic process. Q in and Q out is heat addition or heat rejection process that will use equation Cp or Cv delta T. Okay. So now we try to look what has been given in this example. Given the data given is RV equals 16, where RV is compression ratio V1 over V2, and then we have cut-off ratios. RC is equal to, where cut-off ratio is volume after combustion over volume before combustion. Okay, and then we have P1. We have P1 here, 95 kilopascal, and then we have temperature 1 is 270 degrees Celsius plus 273 Kelvin. Okay, and then we have constant. We're gonna use this constant. K is equal 1.4, and then Cp equal 1.005 kilojoule per kilogram kg Kelvin. Cv equals 0.718, and then we have R gas constant 0.287. Okay, now let's try to solve uh, this. Let's try to solve this example. In this example, they want you to find out the temperature at 3. Okay, heat addition process, temperature at 3. So we know that we have temperature at 1, but we need to find out temperature at 3. And therefore, we need to know first temperature at 2. Okay, so temperature from 1 to 2 is actually isentropic process. First, we need to know temperature at 2 before we can solve temperature at 3. So, process 1 to 2 is isentropic. Okay, isentropic process. So, from the isentropic formula, we know that V2 over V1 power of K equal T1 over T2 K minus K1. Okay, let me see what we have here. Okay, we know that this is actually, we know that this is actually RV, okay? RV, 1 over RV. And then T1, we already have the value. And then we can find out T2, where K is constant, okay? K is constant, 1.4. So from this equation, we will find out T2. Okay, we name it as equation number 1. Okay, so we know that from the process 2 to 3 is a heat addition process where P is constant. Where P is constant. So remember that we have this ratio V3 over V2 is actually T3 over T2. Okay, where V3 over V2 is actually RC. And we substitute temperature 2 that we find out from the equation number 1. We substitute to this second equation number 2 here, to find out T3. Okay, so we have equation number 2 where we can find out T3 by substituting T2 that we from the equation number 1. Okay, so settle first questions. Question number A. Okay, now we can question number B want us to find the thermal efficiency. So the thermal efficiency, you can also use thermal efficiency that given by the formula of compression ratio and cut-off ratio. But in here, I would like to use work net over Q in. Why I use work net over Q in? Because as we can see in question C, is the mean effective pressure, where we need to find out work net also. Okay, so that's why I use work net here. So we know work net is actually Q in minus Q out, and therefore we need to find Q in. Q in is Q in CP. Okay, CP T3 or minus T2. So here we know that we have CP. We already have CP. We already have T3 from the previous question number A, and then we have T2 also solved by equation number 2. So we don't have any difficulties to solve Q in or equation number 3. So now After solving Q in, let's find out what is Q out. Let's calculate what is Q out. In Q out, we know that the volume is constant, and therefore we use CV here. Okay, T4 minus T1. Okay, but as we can see here, we know that we have value for T1, we have constant CV, but we don't have T4. And therefore, we need to find out T4. Okay, we need to find out T4. How to find out T4 is we know that from 3 to 4 is isentropic. Okay, 3 to 4 is isentropic. So we use isentropic formula where T4 is T3 V3 over V4 K minus 1. Okay, remember that V3 over V4 is actually you can substitute by using RV and RC. Okay, you can substitute, and then you will find that it is actually 2 over RV K minus 1. So how can we find this? It's actually V4. Okay, I write it down here. V4 is actually equal V1. V4 is actually equal V1, and we know that, and also we know that V3 is actually 2V2. This is from cutoff ratio. Okay, so when we substitute all these things, that we can and simplify, and we can have this equation number 5. In equation number 5, okay, we take a look that we have T3 values, we have RV given and K as a constant, and from there we can calculate C4. We can calculate the temperature at 4. Sorry. Okay. The last one is that we need to find out. The last question is MEP. Okay, MEP. So MEP, we know that it is a work net over V1 1 over RV. Okay. Okay, now we take a look what we have in this formula. We know that we already calculate for work net. We already know the compression ratio, but we have to find out V1. So as usual, we know that is V1 is from ideal gas formula, PV equal MRT, and then we will get V1 specific volume. Okay, and then we take it at the state number 1 here, and then what we have here, we have P1, we have V1 is what we want to find out, and then R is gas constant, and temperature at 1 also has been given. Okay, that is how we solve example 2.4.